In this tutorial, we're going to focus on a specific paper and on the findings of that paper. So this is a really interesting paper published in 2018 by Wang et al., in which the authors propose that the prefrontal cortex is not only doing reinforcement learning, but it can also be understood as a meta-reinforcement learning system. And the idea is that it basically learns throughout development to be a meta-reinforcement learning agent, and then faced with a new task, it kind of learns on the fly policy for solving that. And so the idea is that basically the prefrontal cortex, along with the basal ganglia and the thalamus, all act together as a meta-learning system. And after training, so you can imagine maybe after development or after you learn a lot of skills, the activations themselves of the system are implementing a reinforcement learning algorithm without necessitating a long-term training, like without necessitating the connections themselves to change through a slow, dopamine-based learning mechanism. In order to illustrate this, in the first part of the paper, specifically in the experiments that are shown in Figure 1 in that paper, the authors basically use an LSTM as a meta-RL agent to perform the simple to unbanded task we discussed previously. And basically, the LSTM needs to make the decision to choose the left arm and the right arm. And you can think of an example episode in which basically the probabilities are 0.6 and 0.4. And in that case, basically the episode is a specific setting of this latent word state, which changes fast. So in the case of this experiment, an episode is a set of 100 trials. So in those 100 trials, the latent word state is fixed, it just corresponds to these episode probabilities. But then the next episode is going to have a different probability setting. They also train these LSTMs in two different settings or in two different contexts. So these contexts are basically a more slowly varying parameter. So they have two contexts specifically in this paper. One of the contexts has the different episodes not related to each other, so they're independent. And so there's no information between the episodes that could be used to better or train faster on the next episode. And the other context is a context in which the episodes have probabilities that are inversely correlated. And so in that case, there is a lot of advantage to keeping some information around in the LCM as you go from one episode to the other. And you're going to see in the tutorial that this is something the model can take advantage. So one part of this tutorial is also to make you see how the resulting LSTM actually does this meta-reinforcement learning. So in the activations of the LSTM, after you train it, and once you deploy it on a new environment, so a new episode, you can see actually basically that this LSTM, without having to be trained again, can just solve this RL algorithm. So we're going to see basically how it solves it, so how it converges on which specific arm to choose. We're going to look at how it performs exploration and exploitation in different types of episodes. We're going to show how basically training in different contexts affects the ability of this LSTM to adapt. And we're even going to look at basically how this learning actually happens by visualizing the internal activations of the LSTM, and showing how it's actually learning under different episodes. And because the weights of the LSTMs are very many, what we're going to look at is a low-dimensional projection of those weights. And this is it. Good luck with the rest of this tutorial, and I hope it is instructive.